The parent extinction killed 96% of all life on Earth in less than 20,000 years. But no known natural process can cause destruction that fast or complete. We assume we're Earth's first intelligent species. But what if we're wrong? What if advanced civilizations rose and fell millions of years before humans existed, leaving only subtle traces in rocks and ice? We're about to explore carbon signatures that don't match natural cycles. Extinction patterns too coordinated for chance and geological evidence that suggests intelligence may have emerged before. Like and subscribe because this investigation challenges our most basic assumptions about life on Earth. Prepare yourselves. We begin, music, in the heart of Africa beneath tons of rock and 2 billion years of silence. Scientists found something that should not exist. Natural uranium ore had somehow arranged itself into perfect nuclear reactors, complete with control mechanisms that prevented meltdowns and waste disposal systems that contained radiation for millennia. These weren't crude experiments. They were sophisticated power plants that operated flawlessly long before the first fish grew legs. The Oklo uranium deposits in Gabon reveal reactor cores where uranium-235 concentrated itself into critical masses, then moderated its own reactions using groundwater as a coolant. Think of it like a campfire that automatically adjusts its own fuel supply and never burns out of control. But campfires don't require advanced physics and engineering knowledge that humanity only mastered 50 years ago. Each reactor produced about 100 kilowatts of power and ran for hundreds of thousands of years before shutting down safely. The waste products remain exactly where they were left, contained in natural clay barriers that prevented contamination from spreading. Scientists studying the sites found isotope ratios that match modern nuclear waste, proving these weren't just random chemical reactions. What makes this discovery truly unsettling is the precision. Natural uranium ore contains less than 1% of the file uranium-235 needed for sustained nuclear reactions. But at Oklo, concentrations reached the exact 3% threshold required for criticality. The probability of this happening randomly across multiple sites is mathematically negligible. Some researchers suggest these formations resulted from unique geological conditions that no longer exist on Earth. The ancient atmosphere contained different oxygen levels, and slower-flowing groundwater could have concentrated uranium over millions of years. But this explanation requires an extraordinary series of coincidences occurring simultaneously across 17 separate reactor sites. The reactors operated during Earth's Great Oxidation Event when cyanobacteria pumped oxygen into the atmosphere and triggered the first mass extinction. This period saw dramatic changes in ocean chemistry and atmospheric composition. Could some ancient species have developed nuclear technology as their world transformed around them? Could they have built these reactors to power underground facilities while the surface became uninhabitable? We find no artifacts, no tools, no clear signatures of intelligence. But absence of evidence becomes less meaningful when you consider the timescales involved. 2 billion years of erosion, tectonic activity, and geological recycling would erase nearly every trace of even the most advanced civilization. Metal corrodes, concrete crumbles, and organic materials vanish completely. Yet the nuclear waste remains locked in rock formations like a message written in atoms. The isotope signatures tell a story of controlled fish, precise engineering, and contained disposal. They represent technology that humanity struggles to achieve even today. If these reactors were built by intelligence rather than accident, we face a disturbing possibility. We might not be the first species to discover nuclear power on Earth. And if we're not first, what happened to whoever came before us? The answer might be waiting in the rocks themselves, written in the language of extinct atoms and forgotten elements. 66 million years ago, a space rock ended the dinosaur age in minutes. But what if some dinosaurs had already built cities, developed agriculture, and started manipulating their environment before the asteroid hit? The Curran hypothesis suggests that advanced reptilian civilizations could have thrived for millions of years without leaving any traces we'd recognize today. Dr. Gavin Schmidt, a NASA climate scientist, proposed this thought experiment to highlight how difficult detecting ancient civilizations actually becomes. He named it after the intelligent reptiles from Doctor Who, but the science behind it is deadly serious. If an industrial civilization existed on Earth 50 million years ago, how would we find evidence of their existence? Consider the enormous advantages dinosaurs had over early mammals. Triceratops possessed brains larger than modern elephants and lived in complex social groups. Velociraptors demonstrated sophisticated pack hunting strategies that required communication and planning. Some species, like their Anosaurus, grew to massive sizes while maintaining herbivorous diets, suggesting they had solved large-scale agriculture problems. The fossil record shows dinosaurs dominated Earth for over 160 million years. That's 800 times longer than modern humans have existed. During this vast period, countless species evolved, adapted, and developed increasingly complex behaviors. Some built elaborate nests, others traveled thousands of miles in coordinated migrations, and many displayed the kind of intelligence that could theoretically support technological development. But finding proof of dinosaur cities poses nearly impossible challenges. Fossilization requires very specific conditions that preserve only tiny fractions of ancient life. Most dinosaur fossils come from creatures that died near water and were quickly buried in sediment. Urban environments, agricultural areas, and manufacturing centers rarely provide these preservation conditions. Even more problematic is the recycling nature of Earth's geology. Tectonic plates constantly move, subducting old ocean floor into the mantle while creating new crust at spreading centers. The oldest ocean floor on Earth is only about 200 million years old. Any evidence of coastal civilizations gets systematically destroyed and recycled into molten rock. Continental surfaces fare slightly better, but erosion, weathering, and sedimentation bury or destroy surface features over time. Mountain ranges rise and fall. Rivers change course, and glaciers scrape away entire landscapes. The Appalachian Mountains were once taller than the Himalayas, but hundreds of millions of years of erosion have worn them down to gentle hills. What about technology that might survive these processes? Modern materials like plastics, refined metals, and concrete would decompose or become unrecognizable within millions of years. Even radioactive waste from nuclear power plants would decay beyond detection in the time scales we're considering. However, certain signatures might persist in the geological record. Large-scale mining operations could leave distinctive mineral distributions in rock layers. Industrial pollution might create unusual chemical concentrations in sedimentary deposits. Mass agriculture could alter soil compositions in ways that fossilize over time. The absence of these signatures doesn't prove dinosaur civilizations never existed. It might simply mean we don't know where to look or what to look for. But if dinosaurs did build technological societies, their fate offers a sobering lesson of the fragility of even the most successful civilizations. If an entire technological civilization vanished from Earth's surface, what traces would actually survive after 100 million years? The answer is both everything and nothing, depending on where you look and what you consider evidence of intelligence. Start with the most obvious markers of human civilization. Cities, roads, and buildings would disappear first. Even our most massive concrete structures would crumble into unrecognizable rubble within several million years. Steel rusts away completely in wet climates within centuries, and aluminum corrodes more slowly, but still vanishes over geological timescales. Glass breaks down into sand. Plastics decompose into molecular fragments, and even our nuclear waste becomes undetectable as radioactive isotopes decay. But some signatures prove surprisingly persistent. Large-scale mining operations create distinctive geological features called anthropogenic deposits. Strip mining copper or coal leaves scars in rock formations that could remain visible for tens of millions of years. Underground mines collapse and fill with sediment in patterns that differ noticeably from natural cave systems. Industrial agriculture might leave the most durable fingerprints. Intensive farming depletes soil of specific nutrients while adding others through fertilizers. These chemical changes get incorporated into sedimentary rocks as soil layers turn to stone over millions of years. A civilization that practiced agriculture for thousands of years could create distinctive chemical signatures spanning multiple geological formations. Urban heat islands represent another potential marker. Large cities raise local temperatures by several degrees compared to surrounding countryside. This warming affects local weather patterns, plant growth, and seasonal cycles in ways that influence sediment deposition. Ancient cities might leave thermal signatures embedded in rock layers like fossilized temperature readings. The most persistent evidence might come from mass extinctions. Human activity is currently driving species to extinction at rates roughly 1,000 times faster than natural background extinction rates. This creates a distinctive signature in the fossil record where diverse ecosystems suddenly collapse and never recover their original complexity. Any advanced civilization would likely cause similar ecological disruptions that persist as gaps in the fossil record. Even more subtle markers exist in carbon isotope ratios. Burning fossil fuels releases carbon with distinctive isotopic signatures that differ from carbon cycled through living organisms. Industrial civilizations would pump massive amounts of this ancient carbon into the atmosphere, creating detectable spikes in carbon dioxide levels preserved in ice cores, marine sediments, and fossil plant tissues. Consider how metal processing might leave traces. Smelting always concentrates heavy metals like lead, mercury, and cadmium in ways that don't occur naturally. Ancient smelting sites could remain detectable as unusual metal concentrations in soil and rock layers. Even after the original processing facilities erode away, the chemical fingerprints might persist. Satellite archaeology demonstrates how subtle traces become visible with the right tools. Buried Roman roads show up in aerial photographs because they create slight changes in soil chemistry that affect plant growth. Ancient building foundations appear as geometric patterns in wheat fields. Archaeological sites reveal themselves through tiny variations in ground temperature detected by thermal imaging. But here lies the critical problem. We're looking for evidence of something we don't understand using methods designed to find things we already know exist. Ancient civilizations might have used technologies, materials, and energy sources completely different from our own industrial approaches. Their footprints might be hiding in plain sight, written in a language we haven't learned to breathe yet. Deep in Antarctic ice cores, scientists found carbon isotope ratios that tell impossible stories. The numbers don't match any known natural process. Yet, they appear consistently across multiple drilling sites and span thousands of years. These chemical fingerprints suggest massive releases of ancient carbon into the atmosphere at times when no natural mechanism could account for such events. Carbon exists in two stable forms that act like geological fingerprints. Carbon-12 makes up most natural carbon, while carbon-13 appears in smaller but measurable amounts. Different processes create distinctive ratios between these isotopes. Plants prefer lighter carbon-12 during photosynthesis, creating predictable patterns in organic matter. Volcanic eruptions release carbon with different ratios depending on the source of the magma. But the mysterious signatures don't match either category. They show carbon isotope ratios consistent with massive fossil fuel burning, occurring at irregular intervals throughout the past several hundred 000 years. These spikes appear suddenly in the ice record, persist for centuries or millennia, then disappear just as abruptly. The timing makes no sense from a natural perspective. Iced ages and interglacial periods follow predictable cycles driven by Earth's orbital changes. Natural climate variations produce gradual shifts in atmospheric chemistry, not sudden massive releases of ancient carbon. Volcanic activity can inject large amounts of carbon dioxide into the atmosphere. but volcanic carbon has distinctly different isotope ratios that don't match the mysterious signatures. Ocean circulation changes can mobilize carbon stored in deep water and marine sediments. During rapid climate transitions, warming waters release dissolved carbon dioxide and methane from underwater deposits. But these natural carbon releases show characteristic isotope patterns that again don't match the anomalous readings from ice cores. Some researchers suggest the signatures result from massive forest fires or peat bog combustion during particularly dry climate periods. Burning organic matter does produce carbon dioxide with the right isotope ratios, but the scale required to create the observed atmospheric changes would need to consume entire continents' worth of vegetation simultaneously. Even more puzzling, the carbon spikes often coincide with other atmospheric anomalies. Methane concentrations spike during the same periods, but methane isotope ratios suggest industrial rather than biological sources. Trace metals like lead and copper appear in higher concentrations during these episodes. Despite no known natural processes that could simultaneously mobilize both greenhouse gases and heavy metals, the geographical distribution adds another layer of mystery. Ice cores from Greenland show the same anomalous carbon signatures at the same times as cores from Antarctica. This global synchronization suggests whatever caused these events operated on a planetary scale. Natural processes that affect both poles simultaneously are limited to truly catastrophic events like massive volcanic eruptions or asteroid impacts.